Okay, so I'm going to get started. So what I'll be talking about today is this problem I have been working on for a few years, which is mesoscale swimmers and active matter in fluids and intermediate Reynolds numbers. And I'll be talking more about this. Feel free to ask me. Go ahead. Oh, nobody's asking anything. Sorry. First, I would like to acknowledge my collaborators in this project and my students, my group, everybody who has worked on this over the years. So this is goes back a long time. So a bunch of people in North Carolina. Can you see my mouse? Yeah.
Yes.
There. Yeah. Thank you. So yeah. So let me go ahead and keep going. So a lot of people in North Carolina, Chapel Hill, but also people who used to be in North Carolina and now have moved on, like Laura Miller and Amit, Chris Rycroft and Nick at Harvard, and some people in the UK at the University of Nottingham as well, where I did my PhD. So, I would like to take a moment and advertise this series, the K-Log W series from the American Physical Society. So I'm involved in this group, the group on statistical and nonlinear physics. And I want to encourage you all to become members, even though it's the American Physical Society. But we have a lot of events and interesting talks online that are for everybody. If you're not aware of them, check them out here on this link. Just Google K-Log W series, American Physical Society, and you'll find our website. And we have a lot of recorded talks online. So it's a very, it's a fun talks presentation series. But there's also a lot more things that we're doing. And if you would like to get involved, feel free to contact me. Okay, and with this, why is it going backwards? Sorry. With this, I would like to get started with this slide that shows a lot of systems that we call active matter. And just to point out a few, so we see a school of fish here. This is a raft of ants. These are natural systems, right? We have things like bacteria down here, biofilm over here. We have flocks of birds, crowds of humans, and also synthetic systems like these robots that are organizing and form these structures. And most of you, perhaps a lot of you, are familiar with this because it's a very big field at this point, but I will go through and just mention a few of the characteristics of what we mean by active matter, what I mean by active matter, because some of the definitions are a bit more subtle. So we usually, when we talk about active matter, we're referring to a collection of motile self-propelled particles where the energy is consumed locally. So that means that each particle has fuel or battery where that it consumes on the local scale. So at the particle or organism scale rather than externally. So if you're applying, let's say, a magnetic field externally. And in a lot of these systems, what we have found is that the interactions are simple, can be fairly simple and local. Local meaning that they're not long range. But yet we get a lot of we can get complex global behavior. And this is what we see in this slide. The school of fish and the organization, the collective behavior of these systems can be quite complex. The other thing that's quite evident is that we see this kind of behavior across length scales and in different environments. So if you notice in my slide, we have things that are occurring in fluids, on the surface of the fluid, on a substrate, with friction, in air, and of course at different length scales, from very small to quite large, like the cars and traffic here. And the thing that I'll be talking about today is the role of fluid environment, not in general, but in a sort of more specific case that is what I'm interested in. But it will be mostly on fluid dynamics. I would like to take a moment and just say that we work on other things, and you can check out my group's website. So one is on active matter mixtures, and this is without explicit hydrodynamic interaction. So this is sort of Brownian dynamics simulations, and also this liquid-liquid phase separation, which is an interesting new topic for me in collaboration with biologists. Okay, but today we're talking about fluids. So I would encourage you to interrupt me and ask me if you have especially clarification questions, if something doesn't make sense. And of course, I'll take questions at the end as well. So the first thing I would like to show you is this plot here, where it's very common in biological fluid dynamics, where we plot the velocity of organisms. So this is about motility. Okay, so thinking about motility in biology, we can plot the velocity of an organism as a function of the Reynolds number, and the Reynolds number is defined over here. So it's a dimensionless ratio of the speed, and in this case of the speed of the organism, times its characteristic length scale divided by the viscosity of the surrounding fluid. And what you can see here is that we have at the low end, low Reynolds numbers, what happens is that viscosity dominates, and sorry, I don't know why this is happening. I don't know why it's going backwards. So at the low Reynolds number, we have viscosity effects that dominate. And here we can make assumptions about our equations and how the fluid is described, which is the Stokes regime. And here we have things like microorganisms, bacteria, cells, and nanoparticles, synthetic nanoparticles. On the high Reynolds number limit, we can sometimes make assumptions that there is no viscosity and that inertial effects dominate. So it could be the inviscid regime. And we have things like birds and whales and ships and airplanes and humans. We operate at the high Reynolds number. But what you can see here is that in between, there's this region that we call intermediate Reynolds number. And this is where we have the influence of both components. And this is not a region where that's empty of neither organisms nor machines or processes that take place. And I have some examples here. So if you roughly to think about what it is we're talking about. So we're talking about organisms or robots or processes where the length scales that are relevant are 0.5 millimeter to say 50 centimeter. And of course, it depends on the other parameters as well, but this is roughly to give you an idea. So this would be things like ciliates and plankton, insects, small animals, as well as small drones and robots that one might be interested to make. And as you can see here, the intermediate Reynolds range is not, and what I'm showing here in the picture are some of these organisms, and there are a lot of weird organisms that operate in this region. So they all sort of use very interesting and strange motility mechanisms. But some of the more well-known ones are dragonflies and jellyfish, but there's also these the brine shrimp, other creatures. Now, the other thing I would like to point out is that this is not only is this not a region that's empty of organisms and things that we might like to make, but also it covers many orders of magnitude. So this is rough. And as you can see here, there are these dashed lines. So it's not clear where that boundary is. What I'm mostly interested in, and what I have been interested in my group for some time, is especially I'm gonna ignore this high Reynolds regime, and I'm focusing on this intermediate regime, but also the transition from Stokes flow into that intermediate range. So one of the questions is, what happens at the boundary? For one thing, where is that boundary? So in my plot here, there is this dashed line. And what we know for flow past the cylinder or flow past the sphere, where the transition from Stokes flow, when it breaks down. So we know when that happens, but we don't know in general for strange geometries, and we certainly don't know for organisms that have strange geometries and are flapping and moving different appendages and so on. So what happens at this boundary? Where is this boundary and what happens? And I would like to say that boundaries are not only not clear, but they can be very important both for biology and for materials. And a lot of this talk, I don't know how many results I can show. I'll try to just motivate you to read my papers. So one of the why is the Reynolds number important, and why is that boundary important? So I'll just give you an example that is not what I'm working on, but it beautifully illustrates what's going on. So this is a paper. This is a paper about larval fish. It's an ecology paper. It's fairly recent, 2014. And what they say in this paper is that larval fish die at a rate of 99% within the few days after their first feeding, after they're born, essentially. And this is a very high number. It has been known for a long time in the ecology community, which I didn't know, but they haven't known that they did not know why. And what this paper is claiming is that the reason why they die is because they cannot feed on their own, and they call that hydrodynamic starvation. Essentially, what they're saying is that the larval fish cannot feed because of their reversibility in the Stokes regime. So at low Reynolds numbers, in this regime where there's zero inertia and viscosity dominates, everything is reversible. And this is an example of reversibility. So this is the fish and this is food. And what happens is that as the fish opens its mouth, the food goes in, and as it closes its mouth, it comes out again. So, this is what we mean by reversibility. And the same thing applies if you have something that does this reciprocal motion, trying to swim, for example, for motility. So it would be going back and forth in the same way as this. So my point is that this boundary is also very important, both for organisms, as we see there in this example, but it's something that we can use because there is a transition at some point from essentially zero inertia, or where we can make the assumption of zero inertia, to something where inertia matters. And we're focusing on motility, so things that are swimming in particular here. So what happens at the boundary? So we have, at the boundary, we see a transition in behavior. So an example was this fish, but we can think about it as immotile to motile. So you can have something here that cannot swim because it would be going back and forth because of reversibility. But at some point, as you increase the inertia, it would start to swim. So this is something that we have worked on and would like to understand more generally. The other question is, what happens for many swimmers? So on either side of the boundary. And what I mean by this is this. So if we're looking at the right side of this boundary, so in the intermediate Reynolds range, I see here, we see different behavior at different intermediate Reynolds numbers. What I mean by this is that because there's no unifying universal behavior in this regime, it is not a limiting case. So it's basically where we say that we cannot make the other two assumptions. So we can't say that viscosity dominates, and we can't say that inertia dominates. And therefore, everything is thrown into this bucket here. But it doesn't mean that throughout these Reynolds numbers in the intermediate regime, that the behavior is the same, is uniform. And in fact, what we see commonly is that what I mean is that what happens at Reynolds 1 is not what happens at Reynolds 10, is not what happens at Reynolds 100. So you see different kind of behavior. And this can have a huge effect when we're talking about many swimmers, right? Because then the interactions change when the flow fields change. And the other question about relating to many swimmers is also on the other side of the boundary. So there's a lot of work, a lot of beautiful work on microscopic swimmers, so small swimmers in the Stokes regime in active matter. And here we have things like I was saying before, like bacteria, and you see very interesting collective behavior when you look at this in this region. What I would like to say, though, is that if you are close to that boundary, and so I'm not talking for the very tiny Reynolds numbers, but usually we calculate the Reynolds number based on a single swimmer. But when we are in this collective behavior world, we're interested in active matter, and we have millions of these swimmers, then it may be important to look for and define another dimensionless ratio like an effective Reynolds number that would take into account how many of these little swimmers we have, to take into account the size of the swarm. This is not something that I have worked on yet. There's some people who have worked on this, but it's not something that is well understood. And the other thing I would like to say as motivation is that the way we're thinking about it in the future is to think of these to think of these systems in these mesoscale active matter systems as materials. So what are the things that we can do? So there's a lot of work in this regime for active matter, and what I would like to encourage our community to do, and this is what we are doing, is to look at what happens as you increase the Reynolds number and where that boundary is and all the rich behavior that we may find on the other side. And the other, finally, what I would like to say about motivation is this idea of hierarchical self-assembly, which has been very nicely described in this paper, this Nature Review paper, Nature Materials Review paper, I think it is, where Needleman and Dojic talk about active matter as a material, and in organisms, and how there's this hierarchical idea of active particles come together and form bigger and bigger units and assemblies. And as we increase in size with hierarchical self-assembly, at some point, the size is large enough that you are in this regime. This was the last thing I want to say on motivation. And all of this stuff is in this perspective article that I wrote a few years ago, and which is very short and easy to read, actually. Okay, so with this, I will just take the last few minutes that I have, which is not a lot, but to show you some of the things that we have done. And what we did, where we started, was to design, the motivation is to design different model swimmers and observe the behavior crossing the boundary, and then in this regime here. So these are some of the models that we have looked at. And the first one, the one I'll talk about briefly, is this reciprocal swimmer here. So this is a dumbbell. It's a dimer, a small sphere and a large sphere connected by spring that do this oscillation. So this is a reciprocal swimmer because the second half of the cycle looks the same as the first half of the cycle. So this swimmer does not swim in Stokes flow, but at some point, as you increase the inertia, it should, because there's this asymmetry. So it will break that and it will start to swim. And I'll just show you an experiment. I'm not going to talk about the experiment, but just so that you have an intuition of what it is we're talking about. So this is the idea. And this is how it might swim. And you can see the reference here and see more details in the paper. But what we are doing is where I'm going to show you computational results. And this is what the mesh, the fluid mesh looks like. This is my timer for 20 minutes. So I'll just take a couple more and show you some results. Okay, so here we are. So this is our swimmer, and the swimming motion is this oscillation. And what I'm going to show you here are these two swimmers, these dumbbell swimmers. The one on the left is at Reynolds 5. The one on the right is at Reynolds 150. So both of these values are in the intermediate regime that we were talking about before. Everything else is identical. So these Reynolds number are different because of the viscosity, change the viscosity of the surrounding fluid. But everything else is the same, as you'll see, the amplitude, the frequency, and so on. And what you see is the vorticity field is colored. So what you notice very quickly is that the swimmer at the lower end of the intermediate regime goes down, and the swimmer on the right at the higher Reynolds goes up. And if you pay attention to the vorticity field, you can see that they're different. So this was a lot of the work that we did try and understand this behavior. And it's all been published at this point. But it's very interesting to see what the velocity for this very simple dimer as a function of the Reynolds number is, if we do it for many values of Reynolds number. So what we see here is that the Reynolds number is 0, it doesn't swim as we expected. And then the swimmer moves with a small sphere on the front, and it increases its speed. So this negative speed going downwards. And then it slows down and it transitions into moving in the direction of the large sphere. So for a very simple swimmer, there's a dumbbell. If you add inertia, or if you allow for inertia, you increase the Reynolds number. We see this already complex behavior, essentially two transitions. So we have a transition from rest to motility, and then another transition from small sphere leading to large sphere leading. And we did a lot more parameters on this and collapsed this transition, tried to understand it, and looked at the fluid flow fields. And I really would like to hear your questions. So I'm gonna skip to the end and say that we have analyzed the flow fields for these systems, and we have a much better understanding of what's going on. And this is in this paper, in the series of papers I will show later. But what I would like to show you is that I would like to show you, because I started with a motivation on active matter, I just want to show you some videos of pairs. So we have started working on pairs, and we put two dumbbell swimmers at various initial conditions, at various initial arrangements. And then we run our simulations and we see what they do essentially. And we can identify a very small number of stable pairs essentially. So you can see here, they form this P pair and then they swim together. In this case here, they form an immotile pump essentially. So they align in this way. And as you increase the Reynolds number, you see the differences in behavior that arise from the difference in the flow field for each of the swimmer, because you have also this, as you see, this transition in the direction as well. So with this, I'm gonna show you this last one, which is showing how structure changes with inertia for many, many swimmers. So this is not a movie, but you can see what I'm showing here. This is for 120 swimmers. And for Reynolds 1, we see these sort of network-like structures. As you increase the Reynolds number, they are more side by side. And as you increase it even more, it looks more a bit like flocking. So they have these small transient clusters that swim together for a little bit and then rearrange. So with this, I think I'm going to reach the conclusions. So what we see is, what I would like to point out, the motivation for this was that we see rich behavior from simple model swimmers, and these nonlinear hydrodynamic interactions can generate different assemblies that may be relevant for artificial or biological swimmers at these intermediate Reynolds numbers. And we can also use these nonlinear effects to design complexity in materials or processes. And this is the main motivation here in applications in materials such as transitions. these transitions, for example, from motility to from non-motile to motile. And these are all the papers that are relevant for this work. And with this, I think I'm done. So I will gladly take your questions. Thank you.